Welcome to this video lecture about calculating the sample size for estimation. We're going to begin with a sample size for estimating a population mean. When we want to know a population mean, we draw a sample from the population and use that to estimate the population mean. The bigger the sample, the better the estimate. So more precise estimates will be provided by larger samples. So the question obviously arises, how large a sample do we need? Well, that depends on how precise we want our estimate to be. So the first thing we must decide is, what margin of error are we willing to tolerate? We call that delta, which is the Greek letter D, and it represents the difference. The difference between the sample mean that we will calculate and the actual population mean that it's estimating. How big of a difference can we tolerate between those two? We will also need a value for the standard deviation, because the sample size depends on the standard deviation of the population. Populations that have a small standard deviation, it's easier to estimate their population mean because the data are all closer to the population mean. Then we have a formula for sample size. So small n represents sample size in statistics, just as capital N represents population size. So n, the sample size, equals 1.96. And of course, that number is there because that's the number associated with 95% confidence, times sigma, the standard deviation of the population, divided by delta, the margin of error we will tolerate, all to be squared. And if we don't know sigma, we'll just have to go and estimate sigma, either by drawing a pilot sample or by referring to some previous study we have done on that same population. So here's an example where we want to estimate the mean weight of the fish at a fish farm. So a random sample of 4 fish was taken. We don't know if this is the correct sample size or not, but at least this sample will give us a standard deviation estimate. And then we will be in a position to calculate how large a sample do we need. So we will principally use this sample to estimate the standard deviation of the population. And then from there, we will go ahead and calculate the sample size that is required. So those are the weights, those are the 4 data in the sample. And the question is, how many fish must be weighed in order to estimate the population mean to within plus or minus 10 grams? So we have decided on the margin of error that we will tolerate. Plus or minus 10 grams is sufficient for our purposes. So we take those 4 numbers and we calculate the sample standard deviation. It's 19.2. So to the best of our knowledge, that's an estimate of the standard deviation of this population. It might not be perfect, but it's the best estimate that we have. So we will use that value to calculate the sample size that is required. We know that delta equals 10. That's the margin of error that we are willing to tolerate. And so we substitute those numbers into the formula for n. 1.96 times 19.2 divided by 10, all to be squared. That gives us 14.16. Now, a sample size must be an integer. And so 14.16 cannot be our answer for how many fish we must weigh. Any number smaller than 14.16 is too small. So 14 is not an appropriate answer. So we always round up to the next integer. So while the formula suggests 14.16, our answer is 15. We round up to the next integer because a sample size must be an integer. And how many observations we must make is an integer. And any number smaller than the number suggested by the formula is too small. So the first sample size that's big enough is 15. So the answer is 15. 15 fish are required in our sample in order to estimate the population mean to within plus or minus 10 grams. By the way, we already have 4 fish that we have sampled. Those are perfectly good fish. So we could just accumulate this bigger sample by sampling 11 more fish, and then our cumulative sample would be big enough. So our original effort wasn't wasted with taking that pilot sample. We're now going to move on to calculating a sample size for estimating a population proportion. So when we want to know the proportion of a population that possesses some attribute, again we take a sample from the population and we observe the proportion within the sample which possess that attribute. Now, we need to have an initial estimate of the population proportion. I know this is strange because the population proportion is the thing we're trying to estimate. And even before we try to estimate it, we need to have some idea of what it is, because that will help us identify the correct sample size. So we may have some knowledge based on previous experience of that proportion. If it's the proportion of defective units from a manufacturing process, or the proportion of voters who support a certain political party, we will have historic evidence to give us an idea of what that proportion might be. If we have no idea what the proportion is, we can simply use as a planning value the value 0.5. Because 0.5 is the most difficult proportion to estimate. It's easier to estimate proportions close to 0 or close to 1 than it is to estimate proportions close to 0.5, because the standard error of proportion is at its maximum when the population proportion is 0.5. So the sample size then, n, is 1.96 squared times p into 1 minus p over delta squared. Again, delta in this formula is in the denominator. The smaller that delta is, the bigger the sample size will be. More precise estimates require larger samples, so the formula is quite reasonable. So here's an example. How large a sample of voters is required to estimate to within 1% the level of support among the electorate for a new proposal to amend the Constitution. This is a new proposal. It's never been around before, so we don't know what the level of support is. So we'll just have to assume that P is 0.5. It's the most conservative planning value that we can use. Our margin of error is 1%, 0.01. So we lay out the problem like this. P is 0.5, that's our conservative planning value. Delta, the margin of error, is 0.01. We write it as a decimal. We substitute those values into the sample size formula, and we get 9,604. It's an integer, so we can just present that as the answer. 9,604 is the answer. That is a large sample. That's going to be costly to survey that many voters. You will notice that with yes-no type data, where we're estimating a proportion, typically we need much larger samples than when we're estimating population means, when we have numeric data, because every sample observation that we make only gives us a yes or a no, whereas numerical data are much richer. So where you have a choice, it's always a better idea to estimate a mean rather than a proportion. But here it is a yes-no outcome, and so we just have to deal with this as a population proportion. You can read more about this in the textbook in section 4C.